All right, we are back at it as we continue the essentials of geometry, the base of everything we need to know. We're going to talk about how we measure segments. We talked about what a segment was last time. We're going to get some measurements and talk about how we use the ruler and also how we can measure things that are given to us in algebraic expressions. Okay. Calvin doesn't agree with doing much work, but Calvin's not as much of a hard worker as you are. So let's get to work now and follow along in your notes. And as always, pause, rewind if you need to catch up or hear something again. So let's get started here. The first thing we'll take a look at is what is known as the ruler postulate. What the ruler postulate says is, let's make a number line like we did in algebra. So we can match up points on a line with real numbers. The real number that corresponds to a point is the coordinate of that point. Okay. So if we take that point, so point A and point B, we'll give it a coordinate. And as we give these points coordinates, all that refers to is just a spot on the number line. So say this is a road. Let's say point A is about 3 miles down the road from a starting location. B is about 7 miles down the road. Now we can use that information to help us determine the distance from A to B. So as we begin to talk about distance, and when we find a distance between points, and we write that as AB, notice there's no line over the top. It's just AB, shows us the distance from A to B. It's the absolute value of the distance between the coordinates. So if I were to subtract 7 minus 3, that's 4. So it's 4 miles apart. If I subtract it the other way, 3 minus 7 is negative 4. So it's a distance of 4 when we take the absolute value. Okay, so that is how we find the distance. So we can find the distance or measure the length of a segment by using a ruler following the same idea. So in order to do that, we just take our ruler, and now we can move that ruler, and as we move our ruler around, we can move that ruler over. It doesn't matter where we set our ruler. So if I set this here, I can go in and measure that. And as we take a look at that, here I'm starting at S, which is at 1, going to T, which is at about 4.9. So the distance there from 1 to 4.9 is 3.9 centimeters. Okay, so we follow that same principle. Just find the start point, end point, and figure out how far apart those are. Okay. Next, let's apply what we know about segment addition and use what's known as a segment addition postulate. So basically what that means is, I'll just give you the definition here, is if I have a point between two other points on the line, I can just add up their segments to give me the full segment length. So for instance, to find out the length of AC, I can just add up segment AB and segment BC. Okay. So if we wanted to apply that in this situation down here, we've got the cities on the map. Tulsa is on a line segment between St. Louis and Lubbock. It is 380 miles from Lubbock to Tulsa and 360 miles from Tulsa to St. Louis. So those are approximate measurements, and it wants us to find the approximate distance from Lubbock to St. Louis. So using the segment addition postulate, we just add up those two lengths, and we would say, well, 380 plus 360 would be 740 miles. If I wanted to travel from Lubbock to go see the Golden Arches of St. Louis. All right, so now let's apply this using this diagram here. So if I wanted to find GH, I know segment FH is 36 as it tells us here. I know segment FG is 21. So we can see that G is on the same line segment as FH. So I see that I've already used up the length from F to G as 21. I know it's 36 the whole way, so that means it leaves 15 for GH, because 21 plus 15 equals 36. Okay, now our friend algebra returns. So we've got a segment AC, which is a length of 4x plus 4. We want to find that exact length. So we know from A to B is 14, and I know from B to C is 3x minus 4. But I need to find this full length here. As I take a look at it, I see that AB and BC combine to give me AC. So I can do the same thing. I can combine 14 and 3x minus 4, and that's going to be the same measurement as AC, which is 4x plus 4. Okay, so you can solve that for x, and we'll check out what x is, and then we can plug it back in to see what we get. So you can pause it and try that on your own. Okay, so if we solve the equation and combine like terms, we can see that we get 10 plus 3x on the left side equal to 4x plus 4. I subtracted 4 from both sides, and then subtracted 3x from both sides to find out that 1x equals 6. So if 1x equals 6, I can plug it back in. So 4 times 6 is 24, plus 4 is 28. Better check my math there, not 30. So AC would be 28. We can go back and check the other sections and see if that fits. This is 14. X is 3. 3 times 6 is 18. Minus 4 is also 14. 14 is 28, not 30. Okay, so that's so we can apply what we know about algebra with our segment addition postulate. Here I just want to bring to your attention some terminology that will be helpful. What we take a look at when we mention equal, that's using the equal sign. We use numbers, is what we're referring to as equal. And we're using AB with no segment markings. We talk about congruence. A figure is congruent if the lengths are equal. So when we talk about congruent, we use the equal sign with a squiggly line over the top. And here we're referring to shapes, not numbers. So we use the segment markings in that case. So in this figure, we have AB is equal to 2. We see AB is equal to AC. Their numbers are the same. But we could say segment AB is congruent to segment AC because their lengths are equal. So in the same way, we can take a look at these figures here. And we have markings. So this marking, this tick mark, shows that this segment is the same length as this segment. They are congruent. So in these figures, this segment is congruent to this one. We use 2 markings to show that it's different from the other figure, but these two are the same. 3 tick marks show that these 2 segments, DF and FG, are equal, so those segments are congruent. So we'll use that terminology as we go forward. Now, if we want to compare segments for congruence, we have these segments on the coordinate plane, which makes it easier to find their lengths. So we can compare for congruence. So if they're congruent, their lengths must be equal. Since they are a horizontal line and vertical line, it makes it easier to find the length. We can just count along the distance. So JK is 1, 2, 3, 4, 5 units. So JK is 5 units. And let's figure out what LM is. LM, as we look, it's 1, 2, 3, 4, 5 units as well. So LM is 5. So we say LM is equal to 5. So they're both equal to 5. Therefore, JK is equal to LM. And we could say segment JK is congruent to segment LM. Notice since we're talking about the shapes, the segments, we use the congruent sign. Talking about their lengths, their numbers, we can use the equal sign. Okay? Now, midpoints and bisectors. Well, I'm pretty sure you can figure out what a midpoint is. It's the middle point of the segment. So it splits it into two congruent segments. So M is the midpoint of AB, so AM is congruent to segment MB. A segment bisector would be now a point, ray, line, segment, plane, anything that intersects the segment at its midpoint. So it splits segment AB into two congruent sections. AM is congruent or equal to MB. So CD, line CD would be the segment bisector. So we can apply what we know about segment bisectors or midpoints in order to help us find segment lengths. So if M is the midpoint of VW, we want to find the length of VM. Well, if M is the midpoint, it means this side, or segment, VM, is congruent to segment MW. So if these segments are equal, let's make their lengths equal to each other. So we've got 4x minus 1 equal to 3x plus 3. So since those are equal, make that a little bit neater. Since those are equal, now we have an equation, algebraic equation we can solve. So try solving that to see if you can find what VM is. Pause it and start it again when you're ready. Okay, so solving the equation, I added 1 to both sides to get 4x equals 3x plus 4. Subtracted the 3x from both sides to get x equal to 4. So if x equals 4 now, I'm asked to find the length of VM. So put 4 in for x. 4 times 4 is 16, minus 1 is 15. So VM equals 15, which if I check my work, MW should also be 15 if I did my work correctly. So 3 times 4 is 12, plus 3 is 15. So yes, it does work. Next, let's talk about midpoint. If we have a midpoint on a coordinate plane, there's a fancy formula that can be used, but sometimes it's easier just to apply what you know instead of just memorizing the formula. Okay, so let's just take a look at this first instance. It says the endpoints of RS are 1, negative 3, and S is 4, 2. We want to find the midpoint M. We'll take what we know about a midpoint. It's halfway between RS. Well, if it's halfway between, well, it's going to be halfway between horizontally, and it'll be halfway vertically. So if we can figure out those lengths either way, that can help us find the coordinates. So if we look from R to S horizontally, we go over 1, 2, 3 units. So the halfway point would be 1.5. So if I go 1.5 over from R, that gives me the x coordinate at 2.5. And if I go a distance vertically of 1, 2, 3, 4, 5, well, half of 5 is 2.5. So I can either go down from here, 2.5, or up 2.5. So let's just go down 2.5 from, we're at the y-axis at 2. 2 minus 2.5 is down to negative 0.5, negative half. Let's double check. Does that seem to make sense? Over 1, 2.5, down about a half. So yes. So that's how we can find the midpoint. Okay, part B gives us the midpoint. The midpoint of segment JK is 2, 1. One endpoint is at 1, 4. We want to find the other endpoint. So we know if we're finding the midpoint, once again, we know the distance horizontal and the distance vertical will be split in half. So I see if I go from J to M, I'm going over a distance of 1. So it means if I go double that, 2. So from 1, I'm going to add 2 more is 3. So K's coordinate will be 3. And my vertical distance is 1, 2, 3, 4, 5, 6. So it's a distance of 6. But I went down 1, 2, 3 to get to M. So it makes sense that if I go down 6 to get to K, that'll be correct. So go down 6 from 4 is down at negative 2. Okay. So applying what you know about a midpoint, just know it's the halfway point, and apply what you know on the coordinate plane to figure out where that midpoint lies. And then you don't need to memorize the fancy formula. Same thing here. We have segment RS, its endpoints at 2, 3, and S is at 4, negative 1. Now we're asked to find the approximate length. Now if you recall, when we were finding the lengths of these segments, it was easier because we could just count horizontally or vertically. When we get a line that is not horizontal or vertical, we have to do a little bit more work to find that. But if you remember the Pythagorean theorem, that'll help you out a lot. So remember, Pythagorean theorem works for right triangles. And remember that rule is a squared plus b squared equals c squared. Okay? And we'll get that more in depth a little bit later on in the year, but this will help us as we're working with distances. So since we have a right triangle, A and B refer to the legs of the right triangle, where C is the hypotenuse. Okay? So if we can find the squares of these lengths, it will be equal to the square of this length. So if I count over 1, 2, so A is 2, so we have 2 squared, plus, well, B, we go down vertically 1, 2, 3, 4, 4 units. So 2 squared plus 4 squared will be equal to C squared. We don't know what that length is. We'll just plug in C for now. Okay? So as we're taking a look at that, now we just simplified. 2 squared is 4. 4 squared is 16. And equals C squared. Okay? Now, as we take a look at that, now we can simplify. 4 and 16 is 20, equal to C squared. So now how do we get rid of the square? You remember that from algebra. We take the inverse operation, square root. So square root of 20 equals C. Okay. Now, if we wanted, we could simplify that down. So think of our factors. So we've got 20 can be a factor of 4 times 5. And we know the square root of 4 is 2. And we don't know the square root of 5. It's not a perfect square. So 2 square roots of 5 would be the exact length of C. But if we wanted the approximate length, we'd have to type that into our calculator because it's an irrational number. In this case, it wants an approximate length. So we pull out our calculator. So I got my calculator. Okay, hopefully you can see that. Maybe not. So maybe I'll pull out a different one so you can see it. Okay, there we go. Here's my electronic calculator. So if you have the same calculator, remember if we want to take the square root of 20, okay, I can type that onto my calculator and simplify that to get about 4.47. We could use the simplified version, 2 square roots of 5, and we should get the same value. Yes, we do. So 4.47 is the approximate measurement. If we take a look at our choices, to nearest tenth, that would be letter C. Okay, so that is how we can find the length of a segment on the coordinate plane. Okay, if you want, there are some rules for the distance formula and midpoint formula. I'll put those on the screen here if you wanted to copy those down. Otherwise, I think it's much easier to just remember, for midpoint, what does it mean? Okay, it means I'm halfway between segments A and B. Instead of having to try to memorize, well, do I add the x coordinates and divide by 2, or do I subtract them? What do I do here? Distance formula, I would just remember Pythagorean theorem, a squared plus b squared equals c squared. Okay, distance formula is there's a lot of values in there. It is really just a simplified version of the Pythagorean theorem, but it just looks more intimidating with all the different variables in there. But if you just remember Pythagorean theorem, it'll work every time. All right, so that is it for today. Work on the practice problems. Yes, you'll get some word problems. Word problems are awesome. So get to apply what you know. If you have any questions, check over the answers online and bring any questions you have to class. That's all the time we have for today. We'll see you later.